Oh my god, what time is it? Sasha, I don't understand complex numbers and I got an exam in 3 hours. Please help me.
Thomas, come on in. I'll show you how it's done.
Look, Thomas, I made a simple PowerPoint presentation on complex numbers. Look, as you can see, a complex number has a real and an imaginary part. The imaginary part involves the square root of a negative number. We use z to denote a complex number. Z is equal to x plus iy, where x is a real number and I is the imaginary number. For a complex number, I stands for the square root of -1. So on a graph, the y-axis would be the imaginary number and the x-axis would be the real number. Complex numbers show up all over the place in computer science and engineering, especially in electrical engineering, as well as scientific computing. Examples include fast Fourier transforms for signal processing and circuit stimulation. They also show up in physics and programming with vectors and trigonometry. Lastly, they show up in fractals.
Oh yeah, now I remember, like in Mandelbrot's and Julia fractals.
Yes, exactly.
Julia and Mandelbrot's set are produced in the same complex plane that Sasha showed me, with the formula f of z equals z squared plus c, where both z and c are complex numbers. For Mandelbrot's set, we set c and evaluate the formula starting at 0 for every point. For example, if we take c equals minus 1.5 plus I, after many iterations, we can see that it diverges. So we would give this point a color, like blue. Another example would be this point c equals minus 1. After many iterations, we can see that it comes back in a loop. This means that it converges. So we would give this point a color like black. This would give us the Mandelbrot set. The black color means that it converges, and the other colors show how fast it diverges. The Julia set is different. It has the same formula, as it has also a set C, but the Z does not start at 0, and we evaluate starting at a certain point. This gives specific shapes for every C's. How they are related is pretty simple. Since they are both in the same complex plane, for every C value in Mandelbrot set, we can associate a Julia set. And if we zoom in really closely in Mandelbrot set, we can see that the Julia set corresponding to it is really similar. So that's how they are related.
So I changed the equation from f of z equals z squared plus c to f of z equals 2z squared plus z plus c, which has a Mandelbrot set that looks just like this. Then I had to choose two complex numbers in the plane, one in the black area, which was minus 0.4 minus 0.009 I, and one in the colored area, which was minus 0.7 and minus 0.16 I. And they look just like this. I know that the one in the black area converges. As you can see, it has a lot of black color, and the other one diverges because it doesn't have black colors. But mathematically, I don't really understand why. Could you explain it to me?
Alright, so first of all, you would take your complex number, let's say we go with the first one, which is inside, minus 0.4 minus 0.09 I, and then you would plug it in the equation, you would sub it for the z value, and then you would arrive to another complex number. Then that value, you would do it again in the same formula, you get to another complex number, and you can do that an infinite number of times.
Yeah.
If you see that the value keeps getting bigger, well then it'll converge, just like in the graph below. You'll see the curve go up like this, right?
Yeah.
But if the value stays around the same thing, then it'll converge, which will give a graph where the curve just like stays pretty much straight.
Okay.
Understand?
Yeah.
So Thomas, what did you learn today about complex numbers and fractals and stuff like that?
Well, you showed me how to calculate them.
Yes.
Then I learned about Mandelbrot set, Julia set. I learned that we could modify them, and I learned how beautiful they become if we change a little bit the structure of the formula.